Good. I'll start anyway. So yesterday we discussed face portraits, and what you can see here is the face portrait for the wall fluid interfaces. So either the wall going to minus M0 or the wall going to plus M0. Now the idea, just a second, I'm gonna close the door here. So the idea about the idea of the wetting problem is that we look for trajectories that end up in the minus M0 state. So the order parameter should take the value minus M0. Suppose that that's phase alpha. And our trajectories could either go directly there, so like starting from this intersection point of our constant of the motion and the wall boundary condition, starting from this point, presumably we are at the local minimum of the interfacial tension, and the profile that we get is one that descends towards minus M0 from a value nearby. And you can see here in the plots, in the profile plots, that we're descending from M1, from the wall value towards minus M0. So this is a non-wet profile, in contrast with one that is wet, which we can obtain using also the intersection of the constant of the motion trajectories with the wall boundary condition, with this straight line here. And that intersection provides another wall value, another M1 from which we can start. And if we start from here, we can go to plus M0, as is seen here above in this profile. But then, of course, from plus M0, we must introduce a plus minus interface by hand, so to speak, because we must end up ultimately at minus M0. That's our wetting problem definition. So we have to compare these two profiles, one which goes directly to minus M0, which is non-wet, and one that first goes to the other phase, permitting the other phase to develop a macroscopic layer called the wetting layer. And then by hand, ultimately very far from the wall, we introduce the interface between plus and minus. And we also take into account its free energy cost, of course. And if the sum of the free energies for going from M1 to M0, and in addition to that, the interface cost equals the energy cost of going directly, then we obtain a so-called two-phase coexistence of surface states. One is non-wet and one is wet. And this coexistence is called the first-order wetting transition, because in going from one state to the other, we will need to make a jump from one profile to another, a discontinuous jump. And this discontinuity is reflected in a jump in the wall values, from this value to that value here. And also this discontinuity is reflected in the first derivative of the surface free energy as a function of, for example, the surface field, or as a function of, for example, temperature. So here below, we have the expressions for the wall plus and for the wall minus surface free energy, and also for the plus minus interfacial tension. So the wetting condition is that the Young-Laplace equation is satisfied with a zero contact angle. And that implies in this picture an equal areas rule, because you can interpret the terms in the surface free energy as integrals over functions that are displayed in this phase portrait, either the parabolae or the straight line. And the equal areas rule is depicted here for a situation that we are exactly at the wetting transition. And exactly at the wetting transition, this upper area here equals this side area here. And that's that is equivalent to asking the two surface free energies for the non-wet and for the wet profile respectively to be equal. And so we discussed in some detail 2 days ago the constrained surface free energy, which you obtain by choosing an arbitrary value of the wall order parameter M1, and then starting from that value, working your way towards minus M0, either directly or via plus M0. And the total cost of such an enterprise is represented by these branches here of this constrained surface free energy. And the extrema of these branches, there are 3 extrema that can be discerned. One is here, local minimum. One is here, local maximum. One is here, local minimum. These extrema correspond to intersections of the constant of the motion, trajectories, the parabolae, and the straight line that represents the wall boundary condition. And we see that some of these extrema are minima, and those are, of course, physically the most interesting ones. And we see that for this particular choice of parameters, we are exactly at the condition that the 2 minima here are equal, amount to an equal value of the surface, to equal values of the surface free energy, and therefore we are at exactly at the first order wetting transition. So this is in words what I have been explaining, and we now go to a situation that is a somewhat different situation, where the wetting transition does not come about through a discontinuity or jump between 2 solutions, but comes about as one particular solution is continuously modified in such a way that there is an incipient wetting layer that grows and grows as we attune the parameters up till the point that this wetting layer becomes macroscopic or infinitely large, mathematically speaking. And at that particular instance, when that happens, we are also arriving at the wet state, but we have done so in a continuous fashion. And there is, for example, the wetting layer thickness that is diverging in this process. And so there is a gradual, say, continuous evolution of the wetting layer thickness towards its infinite value. And so that is called critical wetting. Critical wetting is actually one example of more generally what is called a continuous wetting transition. And in the phase portrait, it can be obtained quite elegantly by choosing the enhancement to be sufficiently large and negative, so that the intersections with the parabolae occur in this manner here. So we have one intersection here with the upper part, and one with the lower part. Now both will provide local minima of the surface free energy, but on different branches of the constrained surface free energy function, which is a function of the order parameter M1. So this M here actually stands for M1. And the values of the surface free energy for arbitrary choices of M1 are depicted here in these 2 branches of this multi-valued function. Now it turns out that the upper one here corresponds to the absolute minimum, and therefore the equilibrium solution, whereas the lower intersection would amount to a profile that first goes to M0 and then is followed by a plus-minus interface. So that would be a wet profile, but it is not yet stable, because the stable solution is the one with the non-wet profile, which in fact is depicted here at the bottom of the slide. And you see that there is an incipient wetting layer developing of the phase, which is the plus phase, but it's not quite yet a macroscopic layer. It would only become macroscopic if we can push this intersection point towards M0, either by changing the surface parameters, H1 or G, or changing the temperature, which would affect the magnitude of M0. So we can achieve wetting in this continuous manner, provided the surface parameters or the bulk temperature is properly adjusted. So this Kahn-Landau theory, which is probably the simplest possible theory for wetting, with two adsorbate phases and one spectator phase, permits one to get quite a variety of wetting transitions, first order wetting transitions and also continuous ones. What we see here in front of us is an example of critical wetting, and you can imagine that if we would tune the parameters such that we would be on the border between a regime where we can have critical wetting and the regime where we can have first order wetting. If you would be on the border of that regime where this boundary condition straight line would come in here tangentially to this parabola and meet the parabola exactly at the point L or M plus M0, if we would arrive at that particular delicate choice of transition point, we would encounter what is called a tricritical wetting transition. So that's a special case where the first order transition regime goes over into the critical wetting regime. So that's also a possibility in this beautiful, simple density functional theory. So let me check for the online situation. Just go to here. So I noticed that Jane, you're connected, I think. If you unmute, you can maybe ask a question or make a remark.
Hi, yes, I am connected. But yeah, for some reason Zoom is stuck, so I have to keep toggling between the call itself and Zoom. So yeah, so unless I have a pressing question, I will not ask. I'll ask right at the end then.
Yes, or you may interrupt me by unmuting yourself, and then I will hear you, and then I'll go to
Okay.
go to see what you're asking. Okay, great,
Okay,
thanks.
you.
So you can mute again then, and I'll go back to my presentation. Good. So as we discussed, we have a simple theory at hand with only a few parameters, and we can ask for, let's say, in a type of homework type of problem, like find out for yourselves, we can ask for a calculation to be done if you have time and if you have enough, say, enough motivation to do such calculation. It would be very interesting to complete it. The calculation would basically be the following one. So you know that for the non-wet situation, the wall minus surface free energy certainly would exceed the wall plus surface free energy because the surface field prefers the plus phase, but the wall minus surface free energy would not exceed yet the sum of the wall plus and the plus minus, because that would be the cost of a wet profile, and we're not yet there. So the wetting problem you can formulate in terms of this spreading coefficient. So when the spreading coefficient is negative, we are in a non-wet state. So although the wall plus interface is preferred because of the surface field, the system will not develop a proper wet profile because the plus minus interfacial tension has to be added on top of that. And the sum of those two will have to be as low as the wall minus surface free energy. And as long as that's not the case, we are in a non-wet state. But we arrive at the wet state when the equality is realized. Now, this poses an interesting problem because we could consider the wall minus interface and look how far we can push it as a stable or metastable state. Because if we keep on increasing the surface field favoring wetting, at some point the wall minus interface will become unstable and will give way to a wall plus minus interface. Okay, so we can consider the wall minus interface in stable or metastable state. And in the mean field theory that we have at hand, we can actually calculate the value of sigma wall minus for equilibrium and also for metastable states. Let me go back to the phase portrait and illustrate this a little bit. Okay, so we go back here to conditions for first order wetting, and maybe even go back to this one here. So you can imagine that here under these circumstances, we could have a wetting transition and the surface free energy of this solution would match the surface free energy of this solution here. But now imagine that we increase the surface field and we raise this straight line. Okay, we raise the straight line. And then of course, these two intersections here will approach one another. And when the straight line becomes tangent here to the parabola, we will actually lose those two extrema. And so the local minimum corresponding to the non-wet state will have coalesced with the local maximum, and the solution will have disappeared. So then we have reached what is called the metastability limit of the non-wet state. So the non-wet state can be considered even when the wet state is stable, in which case the non-wet state could be a local minimum still, but that capacity will be totally lost when we push the surface field even further and get up to the metastability limit of the non-wet state. But as long as we have not reached the metastability limit, we can still talk about the non-wet state and its surface free energy, even though it might correspond to a metastable state. And this possibility, including the extension to metastable states, so stable and or metastable, we will call sigma wall minus star. So the star means that we continue to have the wall minus profile mathematically until we actually lose it totally, because then the minimum and maximum coalesce and there's no longer an extremum. So we go out of the metastability through a saddle point, basically. Okay. So we can define this difference delta sigma star of this sigma wall minus star minus the sigma wall plus. Now the sigma wall plus is always say at least a metastable state, because the wall prefers the plus phase, so there is no frustration or no conflict. So this will always be an equilibrium state. So then the question is, if we impose the plus phase in bulk, the wall plus surface free energy will always correspond to a stable state. However, if we impose the minus phase in bulk, then this surface free energy could correspond to a stable or a metastable state. Now, the upshot of this homework is to calculate for arbitrary values of the surface field and the surface enhancement, this quantity delta sigma star in say proportion to the sigma plus minus. Okay, so because of the spreading coefficient reaching the value 0 at wetting, you can see here that yeah, there's a question.
Yes, sorry, I just wanted to know, for the delta sigma star, you have a minus there. Does that mean that the positive wall is a negative interaction with the negative wall, or it has a negative effect for the negative wall? Is that why we subtract? I mean, I know delta because we're looking for the difference, but can you also interpret the minus in between as a negative interaction between the two walls?
No, there's no interaction between walls here. So the sigma wall minus is the surface free energy for a profile that goes from the wall to the minus phase. And the sigma wall plus is the surface free energy of a profile that goes from the wall to the plus phase. So let me go back to this picture here. Okay. So the sigma wall minus would be the surface free energy of this profile here. And the sigma wall plus would just be the surface free energy of this profile here and nothing else. So not including the extra interface. Okay. But the wetting transition occurs when the sigma wall minus equals the sum of the sigma wall plus and the sigma plus minus. So there are three actors on this stage. One is this surface free energy of this profile. The other is the surface free energy of this piece here. And then the third one is this surface free energy of the plus minus interface. So that is the meaning of these quantities. And the star means that we can still consider this solution even when the wet state is the stable state. So we can still consider this solution as a local minimum of free energy, as long as this intersection and that intersection here are different. But if we bring these two together, then this local maximum will coalesce with this local minimum. Okay, and then this curve will look like this. It will have a saddle point somewhere here, like this, and will look like that. And we'll have just only one minimum left. So as long as we have local minima, we can distinguish those surface free energies. If we lose the local minimum, because here we get a saddle point, look, here's a saddle point, yeah, where this has coalesced with this one, then we can no longer talk about the sigma wall minus, and we have lost the sigma wall minus. There's no longer such a solution physically acceptable, neither as a stable nor as a metastable state. So that's the meaning of these terms. Okay, so I'll continue, and if there's something, you will alert me. So I'm asking you to prove as a homework that the explicit expression for this model for delta sigma star divided by sigma plus minus is this function here of kappa and phi with the 3/2 powers here. Okay, and phi is a reduced surface field in this way, and kappa is a reduced enhancement in this way. Okay, now why is this useful? Once you have done this exercise, you're able to discuss all the situations that can occur, and I will comment on those situations after I've introduced the critical point wetting conjecture, which is an interesting conjecture and which has initiated, or which has ignited, if I can say so, a lot of works and a lot of debates. So it's a beautiful thing to discuss, and it's called also the Kahn argument, and I'll give a cover version of it in my own way. So suppose we have alpha and beta phases as we had before. So liquid or vapor, or two liquids, and suppose gamma is the spectator phase, or gamma is the wall, or gamma could be the air in this methanol cyclohexane example. And let's suppose that we start out from a situation that the alpha gamma surface free energy is greater than the beta gamma surface free energy. You may also start from the converse if you want, but you have to make a decision and start from something, because we want to explored the possibility of wetting. So the alpha gamma interface, say, is less favored than the beta gamma interface. And so the question is, so what will happen if we impose far away from the wall, we impose the phase that is not favored? Okay. So if we impose alpha far from the wall, then maybe the system would like to introduce the beta phase close to the wall, because that's the preferred phase that would give the lower surface free energy. But you see, the alpha phase is already put in the system. And so the only option to put also the beta phase is to put an extra beta alpha or alpha beta interface far away from the wall, because the bulk condition has been fixed to be the alpha phase. You see, in the wetting problem, you always have to fix your bulk condition and then discuss whether you can relieve a frustrated state and replace it by a more favorable one. So if we go back to our three-force equilibrium drawing with a contact line, which you see one point here of this line, you see the three forces. So the surface free energies are energies per unit area, and therefore forces per unit length measured along the contact line. And then in the situation that sigma alpha beta is small, because in this context, alpha and beta are close to their common critical point, are close to the single phase state in which they have become equal. So near criticality of alpha and beta, Kahn has proposed an argument, which is the following one. So if we have a very small sigma alpha beta, then already you know that the Neumann triangle will become very sharply pointed, and we can discuss the Neumann triangle in terms of the Young-Laplace equation using just one dihedral angle, in this case beta hat. So close to alpha beta criticality, we are dealing with the Young-Laplace equation for mechanical equilibrium of the contact line. And this is called the Young-Laplace equation. This we have already discussed. Now, we also know that approaching alpha beta criticality, the interfacial tension between alpha beta goes to 0 as we approach the critical point with an exponent mu. Mu was 3/2 in field theory. We've calculated that. And in experiment for classical fluids, it's around 1.3 in three-dimensional systems. So this gentleman here is going to 0. Okay. But what about the difference of these two when we approach criticality? Well, if we want to maintain the Young-Laplace equation, and this we must do in the non-wet state, then of course this difference will also somehow have to become smaller as we approach the critical point, or at least we are inclined to think so. And this line of thought inspired Kahn to propose a conjecture. So what about this difference? What happens to this difference as the alpha phase becomes more and more identical to the beta phase? So of course, naively, you would say, oh, well, this probably goes to 0 then, this difference, but in what way? And so let's go ahead. So I have repeated the arguments up till here. And Kahn then proposed that this difference, which you can very well think of as the delta sigma star that we discussed in the mean field theory, and we'll come back to it soon, that this difference would also vanish as you approach the critical point with some exponent he called x, or I call x, and he suggested that this exponent should be the bulk order parameter exponent beta, which in mean field theory takes the value 1/2, and which in three-dimensional fluid systems takes a value of approximately 0.3. Clearly a value less than this 1.3 that is associated with the interface. And so this argument would predict that this quantity vanishes, but more slowly so than the other term in the Young-Laplace equation. But if this difference, let's go back to the Young-Laplace equation here, up here, if the difference between these two goes to 0 more slowly than this one goes to 0, and of course the cosine beta can at most be 1 in absolute value, so they cannot change much in the magnitudes of these quantities, then at some point we are going to reach the equality here if we come from the inequality. Okay, if we come from the inequality, then this one is less than the sum of these two, yes. This one individually is greater than this one individually. So if you bring this to the other side, we get a positive quantity. And then the idea is that the quantity goes to 0, but more slowly than this gentleman goes to 0. And if that should be the case, then at some point, this difference between these two should equal what is here. And even if we push up the cosine of beta hat to unity, which is the biggest we can make this difference going to 0 more slowly will still hit that maximal value that this can take. And at that point, there is only one possibility, and that is that the cosine of beta hat takes the value unity at that last moment that we can still keep the inequality. And from that moment onwards, we must lock into the equality, and we must arrive at the wet state. Remember that we cannot reverse the inequality. We cannot reverse the inequality because, as you remember from an exercise some time ago, if you would reverse the inequality and make this larger than the maximum that this can acquire, the forces along the contact line would not add up to 0, and there would be a net force on the contact line. And this is what happens if you would like to say to have this quantity actually exceed the sum of these two for all possible values of beta hat, namely beta hat equals 0, because that's the maximum you can get here. And so if you would try to break that inequality, you would have a moving contact line, and the contact line would start to move in the direction of the greatest force, and that would mean that you're pulling the contact line this way, so you're dragging in the beta phase, and that would be the spreading state. So that would relax to a completely wet state, which is the equilibrium state, in which there is again the equality. So the Kahn argument predicts that at some temperature below the critical point, so still in the two-phase region, at some temperature we must reach the wetting condition, and the non-wet state must become a wet state. So that argument, of course, supposes that there is an exponent here that is less than mu, and of course this supposition is plausible, but of course there is no proof, or there is also room for exceptions, but it is a very interesting, compelling conjecture, and we will discuss it further. So, for example, here are three graphs, three calculations, And remember that in the homework that I'm asking you, I'm suggesting that you calculate this delta sigma star, and delta sigma star we are going to call delta gamma star here in these figures, and that you also, but you have already calculated sigma plus minus, we will call sigma plus minus gamma 0 in these figures. So gamma 0 is the plus minus interfacial tension, which goes to 0 with an exponent 3/2 as you approach the bulk critical point, which is here at the end of the scale. And so the gamma 0 is the same in these three pictures. And that's just the plus minus interfacial tension. Then the delta gamma star is this curve here, or this curve here, or this curve here. Now, in this situation, in the first figure, we have chosen the surface parameters and the temperature in such a way that we encounter a first order wetting transition. And you can see that we encounter a first order wetting transition because the delta gamma star, as long as it is below gamma 0, so let's go back to the equations. As long as this delta gamma star, which is this difference, is less than the sigma plus minus, we have a negative spreading coefficient. Okay, and therefore we have a non-wet state. Yeah, because this difference then would be less or equal than sigma plus minus, which comes on this side, and therefore we have a non-wet state. Now, if delta sigma star would exceed sigma plus minus, then we would violate this inequality and we would necessarily be talking about a non-equilibrium state, which will relax after some time to the wet state. Okay, if ever there is an equilibrium that's going to be reached. And so we have to be cautious and look at the points where delta sigma star becomes equal to sigma plus minus, because that's the wetting transition point. And if that happens, then basically the sigma wall minus surface free energy as a function of the parameter that we are changing, then basically this surface free energy has a discontinuity in the derivative. Okay. And this can be seen here. So the sigma wall minus will have a discontinuity derivative, and so will the delta sigma star, called delta gamma star, will have a discontinuity in the derivative, because you see the equilibrium state is following this branch, and then the wetting transition takes place, and then the equilibrium value of delta sigma or delta gamma, the equilibrium value of delta sigma delta gamma is equal to gamma 0 from here on. So the equilibrium states are the lowest possible values along these curves. And that set of lowest possible values along these curves is a function that displays a discontinuity of derivative here at this point W. And that's why this signifies a wetting transition of first order. And there is a continuation of the delta gamma star here up till the metastability limit, which I discussed, and which is the saddle point extremum, a coalescence of the local minimum and the local maximum in the surface free energy of the wall minus state. So this is the scenario for first order wetting. Now, question: does delta gamma star or delta sigma star, does it go to 0 at the critical point, as in the Kahn argument? because Kahn argues that this should vanish as you approach a critical point. But this quantity stops being an equilibrium quantity here already at the wetting transition. And even if you continue it in a metastable state, which is no longer an equilibrium state, it will stop existing at this point ML. And beyond that point ML, the sigma wall minus surface free energy does not exist at all anymore. So this means that this sigma alpha gamma stops existing long before you reach the critical point. So the situation is even worse than delta sigma going to zero in some fashion, more slowly than sigma plus minus. In fact, it doesn't go to zero at all. It stops existing, and therefore necessarily we must go over into the wet state, because the wet state is the only physical equilibrium state that exists. You cannot even consider anymore the non-wet state. So a fortiori, Kahn's conjecture works under these conditions, and critical point wetting, as it is called, or complete wetting near the critical point in bulk, is necessary under these conditions in this model that we are discussing, which is also the same model as Kahn discussed, by the way. So in that sense, Kahn's conjecture is a fortiori true, and you end up with one single unique state, which is the wet state, as you approach criticality. Now here in the middle picture, we have the critical wetting transition. And the critical wetting transition is one in which one very smoothly joins the wetting state from the non-wetting state. And this is expressed by this delta gamma star meeting the curve gamma zero tangentially in one single point. And in this case, the first derivative of the equilibrium surface free energy is continuous at wetting, no jump in slope. But a higher derivative may well be discontinuous, for example, a second derivative, a jump in curvature. So there still is a singularity, but it is weaker than at first order wetting, and this is called critical wetting. But also in this case, delta gamma star ceases to exist at the critical wetting transition, and from there on we only have one equilibrium state further. So also in that case, delta sigma star does not exist anymore close to TC, and therefore a fortiori Kahn's conjecture is realized, and critical point wetting must take place, even though there is no exponent x and there is no vanishing of this this delta sigma star. But the main conclusion of the conjecture is a fortiori true. Here the situation gets even more pronounced, because here we have a first order wetting transition, just like we had here on the left, with a discontinuity in the first derivative of the surface free energy. But the delta gamma star or delta sigma star can actually be continued up till the critical point, and actually above the critical point in bulk, and we'll come back to that soon, that situation of surface order above the bulk critical point. So here also a fortiori, the delta gamma star does not vanish at all at TC, but retains a finite positive value there. So the situation again favors Kahn's conclusion, even though this is no longer the case, because the delta sigma goes to some constant, some finite constant. But sigma alpha beta goes to zero, so we are bound at some temperature, bound to break the Neumann triangle, and we're about to break the Young Laplace equation. and so we enter into a spreading state and we must go to a wet state in equilibrium. So although the details of Kahn's argument need not be realized, say, in the form that he proposed, his conclusion that near criticality, complete wetting is necessary, and one of the phases will wet the interface between the wall and the other phase. This conclusion is a fortiori realized in this mean field theory. And this mean field theory, which Kahn initiated but did not develop in full, was developed further by Nakanishi and Fisher, and we'll come to that in a second. Now I would like to discuss the wetting phase diagrams that can be found in this mean field theory. And these phase diagrams will invariably illustrate that complete wetting occurs close to the bulk critical point. So let me check online whether something is happening. Everything seems to be very peaceful and in order.
I have a question. I have two questions. Sorry.
Oh, good.
Hello? Yes.
Yeah.
Sorry. So for
Yes.
the previous slide, right? If we can just look at the previous slide.
Previous one, yeah. Here we
yes,
go.
for graph A. Would it be correct to say that because this is temperature dependent, and you mentioned that the delta sigma gamma will at some point stop and then it will go to equilibrium or wetting, would it be safe to say that should we have changed the temperature before the wetting, that it will continue down on the graph for the meta-stable limit all the way to the end if we change the temperature, right? Because this would be for, if we assume same temperature throughout, then it makes sense that, you know, from the meta-stable limit going, then it will follow, of course, of the lower energy trend line, and so it will go to wetting. But if just before the meta-stable limit we decrease the temperature, will the meta-stable will it then follow the trend of the meta-stable limit all the way past the intersection where it tends to wetting?
So are you suggesting that that you would go from A to C maybe, or something like that?
No. So if we're just looking at a graph, right?
And
yeah, graph A. So you see it's two graphs that intersect one another, and the
right.
the delta gamma star, if we just follow that trend line from 0.75, then at the intersection of the gamma 0, then we say that, okay, it tends towards the wetting. So it follows the path of lowest energy effectively. Yes? Am I still correct in saying that? Okay, so if before that intersection we change the temperature, does that mean that we can prolong the meta-stable limit?
You see, temperature is here on this axis, right? This is temperature. Okay.
Yes.
And so this is temperature. So here's the bulk criticality, and here's below temperature below the bulk critical point here. So if we, you see, so if we change the temperature and we follow the equilibrium states, we're going along this curve like this.
Yes. Okay? Oh, okay. Then I must have misunderstood something. Okay, I understand. Thank you.
If you change the surface parameters, okay, yeah, good. Excellent. You have another question, right?
Yeah, so for graph C though, I see that the delta gamma star resembles the intersection that we had when we were looking at the, you know, that the diagram for the eye. And we had that intersection, and we said that that intersection, if it's a straight line, then it's just the surface field, and if it's if it's a y equals some constant straight line, then it's just the surface field, and then if it's a function of if it is also dependent on the extended surface field, then the line is slightly sloped. So I see for the delta gamma star, the line is slightly sloped. So is that line, are we able to then describe using the H and the G values? So the surface field and the extended surface field. So that's my second question.
Yeah, so your question, if I may reinterpret your question, is like which type of straight line in the phase portrait would give rise to this situation? Is that what you're asking?
No,
so
I'm
this
asking
I can tell you.
delta...
So let's go to the phase portrait once more.
Thank you.
Yeah, I'll explain it. So here, if we go back to this drawing, okay, the situation that the delta gamma star goes to a finite value at the bulk critical point and even continues to exist above the bulk critical point, which was not drawn in this diagram C, but we can do that if you wish, corresponds to a situation where this line runs more or less like this, very steep, and with positive G, with a positive slope. Because if you run the curve like this, even if you close the eye by letting M0 go to 0, you will still have intersections with the parabolae. You will still have an intersection out here, and you will still have an intersection out here. So you will still have two profiles that will go from the wall into the critical phase, with M0 equals 0, and that are different from one another, because one of them will have a positive M1 and the other will have a negative M1 by intersecting the parabolae somewhere here. Okay. So for a very strong enhancement for G positive and strong, you have these outer solutions which will persist even when you go above the bulk critical point, at which point you have not a double well, but a single well. Okay. And the single well will give rise to phase portrait, where you just have one parabola like this and one parabola like this meeting here. Okay. So so this situation will amount to solutions that exist above the bulk critical point, but that are different solutions, whether you came from the minus or the plus state in bulk. So these are solutions that display surface order. Surface order, say in a condition where the bulk is in the single phase state. So those are pure surface states. So the surface can have an order-disorder transition, like the surface of a three-dimensional easing model, which is itself a two-dimensional easing model, can also have a phase transition, depending on the surface couplings, even when the three-dimensional model is in the single phase state. Okay. So for a very strongly enhanced coupling, so for G positive, you also have the possibility of continuing the delta sigma star above the bulk critical point. So in that case, also delta sigma star continues to exist and does not vanish at DC.
Yeah.
But this makes Kahn's conjecture even stronger, right? This makes Kahn's conjecture stronger, because Kahn could just as well have said, let this be an exponent less than mu, or let this even be, let this even go to a finite value, non-zero value at TC, in which case, of course, then also necessarily the wetting transition must take place. Okay, very good. Yeah, thanks for those questions. Excellent. So a little bit more generally now, I am sketching 3 phase diagrams. One is one variable here is temperature, as before. So the critical point is at this end, bulk critical point. Then the other axis is the surface field. So here we have a positive surface field, but we also could have a negative surface field. And the situation, as you see, is completely symmetric. And the difference between these 3 phase diagrams lies in the differences between the values of the enhancement, G. Okay. So if we have no enhancement at all, G equals 0, then this wall boundary condition is a horizontal straight line. And that was the case, for example, here in this, that was the case over here. So this belongs to G equals 0 situation. We have a first order wetting transition, and the locus of those transitions in the H1 temperature plane is then a straight line like this. So imagine we're coming from a point over here, and we drive the temperature towards the critical temperature. Then we will cross the phase boundary, which is called the first order wetting transition, from the partial wetting to the complete wetting state. If the surface field is negative, we could talk about drying instead of wetting if we wish so, and we would go from partial drying to complete drying as we cross that line. You see that Kahn's conjecture is realized because we always go from non-wet to wet state, from partial wetting to complete wetting. So partial wetting is synonym for non-wet, and complete wetting is synonym for wet. Okay. So we have what Kahn called critical point wetting. So closer to the critical point, we go over to the wet state. And for positive values of the enhancement, we have a similar situation, except that this line is curved now. It comes in with tangentially here to the 0 surface field axis as we approach the bulk critical point. Respectively, the surface character under these conditions at bulk criticality is called a special transition here for the surface. And here is called the extraordinary transition for the surface. And for negative enhancement, for G negative, where we have 2 possibilities, first order wetting, the solid line here, or the dashed line, which is the critical wetting transition, which I discussed. So for negative G, it means when you have a slope of your boundary condition line that goes like this, you encounter the possibility of critical wetting. And as you go towards the critical point, so this point moves to the left, and this point moves to the right. This line we leave unchanged. And then this point will evolve towards this point here. So these 2 points will merge as we increase the temperature, and this will signify that we are at critical wetting. Okay, that the wetting layer thickness has diverged, and so this dashed line here is a line of critical wetting transitions. And it comes in with a square root singularity here near this point O, which signifies the ordinary surface transition. So O, S, and E are new concepts for us now. They have nothing to do with wetting, but they have to do with the conditions at the surface when the bulk is critical. So the extraordinary transition means that the surface couplings are enhanced and the surface is capable itself of an order-disorder transition, although the bulk is disordered. The special transition is the coincidence of bulk criticality and surface criticality. It's a very special point. And the ordinary transition is such that the surface has no particular order or no particular capacity of an order-disorder transition at the bulk critical point. So this is the case for surface couplings that are not enhanced relative to the bulk coupling. So these are three very generic, very typical phase diagrams. And they are not only valid, say, for this mean field theory that we have scrutinized, but they also pertain to, for example, simulations of the three-dimensional Ising model wetting transitions. So the Ising model with a surface, a two-dimensional surface, and then a semi-infinite lattice with surface field, surface couplings, and bulk couplings, and many more systems, even systems with long-range forces, which we did not discuss here explicitly, but fluids with van der Waals forces, which also a very important class of systems, will also to some extent show this type of phase diagrams when we study wetting. And so this mean field theory was put into a broader context by Nakanishi and Fisher, and I'll come to that in a second. But just before doing that, I want to show another representation of the wetting phase diagram in which I have rescaled the variables so that I take a certain combination of surface field and temperature, which I used to call phi previously, and another combination of enhancement and temperature, which is this ratio G to M0, which I called kappa in the homework problem that you still have to do. Don't forget. And so in this global phase diagram, everything is compactly rescaled so that there are only actually 2 or 3 curves to be drawn. And PW is the region of partial wetting or non-wet states. Now, if we increase surface fields or bring the temperature closer to bulk criticality, we are going to go up in this phase diagram, maybe like this, and we're going to have the possibility of a critical wetting transition towards the completely wet or say wet state. We can also do this perhaps along here, and then we would be crossing the first order wetting boundary. And remember, the first order wetting boundary permits one to also study a metastable state. And the metastable state will continue to exist until we reach this metastability limit at which delta sigma star stops to exist altogether. So in fact, what we can say is that crossing here or crossing here somewhere, we go into a regime where wetting is necessary. We cannot escape. We must go to the wet state. And also here, when we would cross here, we go into the wet state. But if we go far out on this side with a strongly enhanced surface coupling, we would continue to have the also the metastable non-wet state in the game, and even going towards the bulk critical point and even above the bulk critical point. So that is a region here where we would go somewhere like this out and continue. So this is a very compact phase diagram in which you also notice the point TCP. And if you have listened well to what I have said some 20 minutes ago, perhaps, this is nothing but the tri-critical point. It's the point of transition between critical wetting transitions and first order wetting transitions. It has its own singularities, its own critical exponents, and so on. It's a very interesting point. but very hard to get to experimentally because it just it's so delicately tuned that you may that you are bound to miss it. If you undergo wetting, you'll either do it here somewhere or here somewhere, and rarely or never exactly at that particular place. So I'm about to conclude this theoretical considerations of wetting phase diagrams, but first I want to explain a little bit better these points at bulk criticality, O, S, and E, and maybe some others. And for this, I'm going to a phase diagram which is borrowed from the semi-infinite Ising model in zero in zero surface field and zero bulk field. So this is useful to see, because also here you note that these points O, S, and E are found at bulk criticality, but in zero surface field, and also in zero bulk field, because I did not say, but but would better have said that the bulk field is zero under all these circumstances, because we consider up to now bulk two-phase coexistence. Okay, so here two-phase coexistence. So this implies that also the bulk field is zero, so fully symmetric between plus and minus. Now, except for the bulk condition, which is chosen to be either minus or plus, right? If we choose it to be minus, we can discuss wetting. If we choose the bulk condition to be plus, we can discuss, yeah, you got it, drying. Excellent. Now, we go on. So here, what is this? Okay, in the Ising model, we have bulk couplings reduced by KT. So they're called K bulk. Okay. Now, what are these bulk couplings? Okay, you remember that we discussed the Ising model here. Okay. So here, these GJs are these bulk couplings. And JS, or maybe sometimes called J1 or something, are the surface couplings. And so those are the couplings we are talking about. And let's go back now to this phase diagram. So here we have the bulk coupling. So as you see, you can crank up the energy and go this way, or you can also lower temperature and then also go to the right. So at high temperature, we are in a disordered bulk, okay? At low temperature, we are in bulk two-phase coexistence. So below Kc bulk, we are in bulk disorder. Above Kc bulk, we are in bulk order. But what about the surface? So the surface is just this plane with these enhanced or dehanced couplings. And we know very well that if we switch off the bulk coupling, we just have a two-dimensional Ising model, not a three-dimensional Ising model. We only have the surface there. But that surface, of course, is a two-dimensional Ising model, and it certainly has the capacity to have an order-disorder transition and have a critical point. Due to Onsager. Onsager proved this and did all sorts of wonderful things more than that. And so this point here is the critical point of the two-dimensional Ising model without any sort of bulk three dimensions attached to it. But as soon as we're going to attach some very small bulk couplings and attach a three-dimensional semi-infinite system on top of this two-dimensional surface, we still have the possibility, no surprise, to have order-disorder transition. But you see that because there are couplings now, and all are supposed to be positive and ferromagnetic couplings, because there are couplings now in the third dimension, helping the system to order, the critical values for the coupling, the critical value for the coupling will actually, for the surface coupling, you see Ks, yeah? So the critical value for the coupling in the two-dimensional system will be lower which means that we will shift the criticality to higher temperatures, because this is the high temperature region here. So we shift criticality to higher temperatures, we make order-disorder transition, we enhance its occurrence by introducing a three-dimensional construction on top of this three-dimensional surface, all with ferromagnetic couplings. No matter how weak, we still have an increase of the criticality of critical temperature, decrease in the K. And this continues, and you see, when the bulk three-dimensional system becomes critical, that is, of course, a very important point, because you see, when you reach that point, the surface is no longer going to be able to say, okay, I'm going to order and disorder independently of the bulk. No, the bulk itself will undergo the plus-minus order-disorder transition and will from there on treat the surface as a slave that has to follow this bulk trend, unless there would be competing couplings, which are not the case here. So this surface criticality under bulk disorder conditions will terminate at the bulk criticality, where bulk order and disorder starts. So in that point, that very end point of this line of critical points here is called the special transition. For couplings, surface couplings stronger than those of the special transition, we speak of extraordinary surface transition at bulk criticality. And for surface couplings less than this special value, we speak of the ordinary surface transition at bulk criticality. So these S, O, and E are all only at bulk criticality. Okay, that's the definition of those things. So now you understand the simultaneity of the possibility of having surface criticality and bulk criticality. You also understand the simultaneity of having bulk criticality but surface non-criticality, but surface order plus or minus, okay, at bulk criticality. See, because the surface is ordered for couplings greater than those on this line. So even at bulk criticality, we can speak about the surface order or surface phase separation into plus and minus. And therefore, there are two profiles that exist at bulk criticality. And those two profiles are like a plus surface going into a single phase bulk, critical bulk, or a minus surface going into single phase critical bulk. Now, those two profiles would have exactly the same surface free energy if and only if there is no surface field breaking the symmetry. So if in addition to what we have drawn here, we also take into account the surface field, then we can have situations that those two profiles, oh, I have to change change the battery. Just a second. I'm going to spend 1 minute on that. I'm back. So those two profiles that can exist at and above bulk criticality may have a different surface free energy if and only if there is also a surface field breaking the plus-minus symmetry. And that was the situation. That was the situation here in picture C, when the delta gamma star pertains to the difference of those two states with surface order plus or surface order minus at bulk criticality in the presence of a non-zero surface field. So that's that situation there. Now, to conclude, I'm going to show you beautiful drawings made by Nakanishi and Fisher in a PhysRev letter in 1982. And these phase diagrams have guided numerous works by other people and also by themselves, numerous further work on wetting. And so these are like global surface phase diagrams for various choices of enhancements in the space of temperature, here called small t, and surface field called H1, and even the bulk field called H. So you will recognize in these surface phase diagrams the sections corresponding to zero bulk fields, and those are the sections in these rectangles, and those correspond to the phase diagrams I've shown here, as you will recognize. So first order wetting, tricritical wetting, critical wetting, and here all over first order wetting. And also you will see that there is a possibility to continue above bulk criticality in the case of enhancement, in the case of positive values of G. And that pertains to the surface order under circumstances where the bulk is in single phase state. Now, what is now extra here in these diagrams, and what makes these diagrams even more interesting than everything considered so far, is that also the bulk field is included here. And so that means that we can go out of two-phase coexistence in bulk and still consider kind of wetting phenomena involving the surface states near the wall, although the bulk is in the single phase state. So the bulk could be in a minus state, for example, okay, here. And still we could cross this wing here, and this wing is a surface of phase transitions called pre-wetting transitions. Actually here we see a line here that is precisely the pre-wetting, a boundary of the pre-wetting surface that meets the wetting transition phase boundary at the tricritical point, at the tricritical wetting point. Now, this may sound like a whole lot more detail than we would like to consider here, but let me just allude a little bit to the physics of the pre-wetting transition. So suppose you have a minus phase in bulk and the plus phase is nowhere near, but you put a positive surface field. Then the surface will have some propensity, some eagerness, if you like, to develop a small plus layer near the surface. But there is no way that that plus layer could ever become a macroscopic wetting layer because the plus phase is not stable in bulk and the plus minus interface doesn't exist. But still, there could be a small wetting film of plus, film of plus spins close to the surface when the surface field is positive. And then that film will gradually go over into the bulk minus phase. But it's possible that if you are not so far from the conditions that the plus phase becomes also stable in bulk, that you could have something that is premonitory, that is kind of anticipating the wetting transition that would occur if you would be at bulk to phase coexistence. But the wetting transition cannot be realized in full unless the plus phase also becomes stable in bulk, and so unless the bulk field is zero. But still, at non-zero bulk field, when the minus phase is stable in bulk, you can have a first-order phase transition between two surface states. One surface state is that in which there is a small plus wetting film, and the other state is one in which there is a much thicker wetting film. And that possibly can arise in the form of a first order phase transition, discontinuity of slope of the surface free energy. And then if that happens, you can follow that, what is called pre-wetting transition. You can follow it towards bulk to phase coexistence by letting the bulk field go to zero. And if you would do that, you would see that you would converge to a state in which there is a wet, in a state which is wet, in which the thick film of the pre-wetting transition has a thickness that grows and grows indefinitely as you approach bulk to phase coexistence. And so that indefinite growth of the wetting film that is observed as a function of the bulk field going to zero, that divergence of the wetting film thickness as the bulk field goes to zero is a phenomenon that is called complete wetting, and the approach to complete wetting. And it has its own interesting singularities in the free energy, its own interesting critical exponents, if you like. And so it's a very interesting phenomenon, and it looks very innocent because the state at two-phase coexistence is wet, but then you take it a little bit off of two-phase coexistence and you enter into a pre-wet state that is included here in these phase diagrams, these famous phase diagrams of Nakanishi and Fisher. And there are all sorts of other things that we can say about these phase diagrams, but that's not necessary at this particular time. Great. Now this is, I think, is a good time. So it's 3:30 almost. It's a good time to pause a few minutes, because now I would like to go back from two phases and a wall to our original, more ambitious problem of three phases treated on equal footing. Three phases treated in such a way that there are no wall boundary conditions, no surface field surface enhancement, but the three phases with their own bulk characteristics interplay such that non-wet states are possible and such that wet states are possible. And so treating those three phases on equal footing restores completely the philosophy of the Neumann triangle in its full glory, okay? And so we're going to discuss a model and also experiments in which three fluid phases are treated on equal footing, and we're going to study those systems in the vicinity of bulk criticalities that we could conceive. We could make any one of those two phases out of three phases, we could make them become identical, which would amount to criticalities. We could even be very ambitious and want to make all three phases identical at a common criticality called tricriticality. Okay, and so we're going to do that. We're going to do all of this, at least theoretically, and experimentally we're going to do part of this. But before this, I want to introduce a 5-minute break and also check whether there are some urgent or less urgent questions. Okay, so this is the break. I'm going to take advantage of the break to have a cup of coffee. And so everybody there in the audience, please fire your questions. Jane, Vincent, Shane, and Renee, and who knows who's there. If you want to ask a question, you better unmute yourself. Okay, I think that everything was sufficiently incomprehensible so that no questions are possible. And in this case, we proceed here. As promised, we go back to three-phase equilibria. And let's check Gibbs phase rule. That's always a good thing to do. So Gibbs phase rule tells us that the number of freedoms in thermodynamic fields, thermodynamic variables, you could say, is the number of components minus the number of phases plus 2. So let's ask the question, if we take 3 components, which for our purposes is an ideal situation actually, and we want to have 3 coexisting phases, then what freedom is left? What freedom is left here? So, well, we seem to have 2 freedoms left. Okay. So that would mean that we could talk about a surface of such states in a higher dimensional space. Now, what would be the dimension of this higher dimensional space? Well, with 3 components means that we would have 3 chemical potentials to control the concentrations, right? To control the composition of this mixture. And we, of course, we have temperature, but we also have pressure. And so we have 5 thermodynamic say fields here. We call those things fields, pressure, temperature, and the chemical potentials. In contrast with densities, densities would be density, number density, mass density would be concentrations, and so on, polarizations, and so on and so on. But we have here 5 thermodynamic fields. We're not considering electromagnetic fields in addition. We could, but we're not doing this here, and so on. So just 5 basic thermodynamic fields. But wait a second, we want to be in thermodynamic equilibrium. So there is a single equation, an equation of states, which involves those 5 variables. And so we have 4 variables that are left in equilibrium. And if we just figured out that we have 2 freedoms, if we want to have 3-phase coexistence with 3 components, so there is somewhere in this 4-dimensional equilibrium state space a 2-dimensional surface. And so we will be able to choose 2 2 active variables, or you name them 2 variables of particular concern, in the space of which we can draw a certain area which would represent those 3-phase coexistence states. Now, we ask for more, because we want also to have the possibility to have 2 of those phases identical at the criticality condition. And that means that we will go to critical endpoint. Such condition is called the critical endpoint. Why? Because there is the coexistence of these 2 phases that have become identical into a critical phase, and the remaining 3rd non-critical phase. And so that is called a critical endpoint. And even having higher aspirations, we will try to find a point where those 3 phases become identical at the tri-critical point. But that would mean that we would have gone down from 2 freedoms to 1 freedom for the critical endpoint lines to a single freedom for a to 0 freedoms for the tri-critical point. Now, the fact that there's 0 freedoms left for the tri-critical point means that in this space there's only 1 point that is a tri-critical point. But it also means well, it does not necessarily mean that there's only one such point, but it certainly means that there is not a continuity, not a continuous set of such points. There could be maybe 2 or maybe 6 tricritical points in this space without violating Gibbs phase rule. Okay, because 6 points is still 0 freedoms. To have a freedom, you need to have a continuously varying parameter, so you have to be able to trace at least a line for 1 freedom, a surface for 2 freedoms. So let's be careful, but let's assume in our context that we're dealing with systems with just 1 tricritical point, which is good enough for our purposes. Now, here is a representation of such a 3-component or ternary mixture in what is called a composition triangle. So the composition triangle is a representation in which we can draw such a two-dimensional area corresponding to 3-phase coexistence states. And if you look at the picture in the very middle here, which is a picture which, as all of the pictures here, are at constant pressure, say ambient pressure, but the pictures differ because temperatures varied. But at some particular temperature and pressure, we can draw an area of 3-phase coexistence states. And what does this mean? It means that if we would try to realize a certain state here, which indicate by the arrow, in this composition triangle, it would mean that we would have a certain state, say, which would correspond hypothetically to a homogeneous state of concentrations of A, B, and C, A being water, B being oil, C being amphiphile in this example. But inside this area, the states are not realizable as single homogeneous states. Because any such point inside such triangle will decompose into a state which is rich in A, a state which is rich in B, and a state which is rich in C. Likewise, if we would go on the boundary of the 3-phase coexistence region, which is this area here with 2 freedoms, we'd go, for example, here on this line. And on this line, if we choose any point on this line, the system will split up into 2 phases. One which is rich in A and one which is rich in C, and also has some B, but the 2 compositions are indicated by these 2 endpoints on this line here. And so on. And so when we would arrive at this particular point here, at this particular composition, we would be at a critical point. We would be at a critical point where 2 of the phases have become identical. And we would not have a 3rd phase present because we would be outside of the 3-phase region. If we want to be at a state inside the 3-phase region, at which a non-critical phase coexists with a critical one, we would have to go towards this figure here, which is the limit of this situation for the triangle shrinking here and bringing this criticality exactly in equilibrium with the 3rd phase, which is non-critical and which has this particular composition here. This would be a critical endpoint state, and likewise there's a critical endpoint state down here below at the so-called lower critical endpoint temperature, in contrast with this upper critical endpoint temperature. So varying temperature across thermodynamic space here, we encounter 3-phase coexistence and explore 3-phase coexistence between 2 limits, between 2 critical endpoint states. called upper and lower critical endpoint. So this is what can be achieved, for example, by varying one of the thermodynamic fields. Okay. Now, the experiment that we consider here was performed in the late 80s and by Carl White and Busser. And they studied mixtures of water, non-ionic amphiphiles, and non-polar solvents. And so basically the latter are oil. And they considered situations where you have lenses or droplets of what is called the middle phase between the outer phases. So in the gravitational field, like in a good laboratory, we would have the A phase here down below, the B phase up here, and then the middle phase C in between. And the situations that they consider is, for example, water-rich and then oil-rich here, and then amphiphile-rich phases here in the middle. And they consider varying the temperature in such a way that three-phase coexistence states are explored. And you can see here that there is good three-phase contact. And we can distinguish the dihedral angles here, as we did in this discussion of the Neumann triangle. And we can go to a critical endpoint of this type, the upper one or the lower one. Reaching the upper critical endpoint, we can do that by letting the BC interfacial tension go to 0, in which case the AC interfacial tension will approach the AB interfacial tension. And so these are situations with liquids, fluids, where we have very often the situation that we do not enhance surface couplings in any particular way. And we also do not have wall boundary conditions or something that could be reminiscent of the discussions that we had about metastable states or so. So we can conjecture that these two interfacial tensions will become identical at such critical endpoints. Of course, we will have to test everything, do measurements, and so on and so on. And this will come, and also do model calculations. But this is a very good, say, first step. So we have a situation of an upper and a lower critical endpoint. And we're going to ask the question, what happens to the difference of these two surface free energies as one of the other, as the other is going to 0, as the third one is going to 0. So that's a nice question, and we can in the few minutes, say 10 minutes that are left, we can discuss, say, following the line of argument of Carl White and Busser, can discuss the situation. At the same time, bringing in the Kahn argument, because Carl White and Busser were very well aware of the Kahn argument and actually try to put it in a more general frame and even consider the possibility that the Kahn argument is reversed. And they needed to suppose all these possibilities because otherwise they could not make any sense of their experimental findings. So let's follow Carl White and Busser a little bit. And they said, okay, approaching BC criticality, look here in this bigger figure here. So BC, the BC interfacial tension is very small. The AC is large, the AB is also large, and we come to a situation where one of the dihedral angles becomes pi, and the A phase is almost undeformable in the sense that the lens that is on top of it doesn't make a bump or so in it. Huh? So we're going to a situation where we can describe everything nicely with a very sharply pointed Neumann triangle. So approaching BC criticality, the BC interfacial tension vanishes with an exponent mu. That's old news. And the delta sigma, remember the delta sigma is sigma AB minus sigma AC here, is presumably positive, could also be negative, doesn't really matter. It depends on which criticality you're considering, or whether you're considering contact angles that are small or contact angles that are large. So all the possibilities there. But here we assume for the time being that we don't have to know the sign of this difference, and just it is proportional to something that, according to the Kahn argument, would vanish with some exponent. Now, the first case that these gentlemen, Carlwright and Busse, consider is that x exceeds mu. Wait a second. If x exceeds mu, that would mean that we do not reach the wetting condition, because the Neumann triangle will always be closed and will always be non-collapsed. So this difference then goes to zero faster than the interfacial tension. So if we then look at the cosine of the angle C hat, for example, we would obtain that it vanishes as we approach this critical endpoint. So this would just mean that this angle would go to 90 degrees, that this contact angle here would go to 90 degrees, which in the figure it almost does. And it's at the level of the Neumann triangle, this scenario would correspond to the Neumann triangle becoming isosceles before it collapses, or at the same time that it collapses, so to speak. And that would result in a 90-degree contact angle as we approach the critical endpoint, so no wetting at all. To the contrary, 90-degree contact angle, which is a neutral value for the angle. So this is the first possibility that they consider. And then the second possibility they consider is exactly the condition that uttered, proposed, conjectured by Kahn. And that is that x is less than mu, and that the cosine of C hat then goes to unity at some temperature before we reach the suspicious critical endpoint. And so in this case, the Neumann triangle will collapse, as we know, before we reach the upper critical endpoint in this case. Now, interestingly, the experimental observations of Carlwright and Busse in the particular system under consideration, approaching either the upper critical endpoint or the lower critical endpoints, the experimental observations of Carlwright and Busse are not consistent with case 2. They're not consistent with the Kahn argument because they do not find wetting in the particular system under consideration, neither near the upper consolute point, upper critical endpoint, nor near the lower critical endpoint. Now, question for you, you in the audience online, everybody's now listening with utmost concentration. Is the Carlwright-Busse conclusion, by the way, they concluded using their arguments, using their observations to the best possible accuracy, using glasses or maybe some other means. They didn't do it in much detail, at least not reported it in much detail, but they concluded that the contact angle that they observe is going to 90 degrees. Here and also here in this other situation here. So their conclusion is a 90-degree contact angle based on everything I've said so far. Is this conclusion that the contact angle approaches 90 degrees inescapable. Knowing what is here on this slide, and knowing that they looked semi-quantitatively to the angles in their experiments. Question to you. So I give you 30 seconds now to contemplate and to answer this question: is this conclusion that it should be 90 degrees inescapable given the information that is present here? Let me look online how many people are now triumphantly finding the answer. So how about Vincent? Vincent, can you tell me what is missing here, or what or what we should consider?
Sorry, this for the audience. Vincent is 2 years old and he's gone down for his nap. What is it inescapable that it is 9 degrees? So honestly, I would say that it is inescapable, but it is only considering what is on the paper, because sorry, I'm also driving right now. So can I just conclude that it is inescapable? I cannot look at the screen right now.
Or you can just say what you think.
I'm still driving. Yes, it's no, there was something that caught my eye, but I can't focus on the screen right now.
Do you want me to recap a little bit the argument?
Yes, please. There was the.
So Calvert and Busse say, case 1, x is greater than mu. Conclusion, the contact angle should go to 90 degrees. Case 2, x is less than mu. Conclusion, we should go to a wet state. The experiment contradicts case 2.
That it should go to a wet state.
Yeah.
But then the two solvents are immiscible, so they do not mix. Hello, have I lost?
Yeah.
So
they find that there's no wet state, that the lens persists, and they conclude that the contact angle must then be 90 degrees.
But the two solvents that they're using are of very different densities, correct?
Very different what?
Densities.
Different densities. They have slightly
like
different
water
densities.
And oil. Okay, so it's not like water and oil. So maybe it's something like.
Let me give you a hint.
Methanol. Yes.
Let me give you a hint. So they say there are two exponents here, x and mu, and they consider case 1, x is greater than mu.
Yes.
And in that scenario, there is 90-degree contact angle necessarily.
Yes.
When you approach the critical endpoint. And then they say case 2, x is less than mu. And in that scenario, the contact angle should go to 0 or to pi. And so there should be a wet state. But they do not observe wet state. They observe that the lens persists. And so the contact angle persists, and that they conclude that the contact angle must be 90 degrees.
But there is no case for when x equals mu.
Aha. Very good. Now, now we are in business. Thank you. I think Vincent was whispering this to you, isn't it? I heard him say.
I think so. I think so.
I heard him say x is mu or something, right? Yeah, that's what he said. So good. So fantastic, Vincent. You will become a famous scientist at some point. And so x equals mu. They omitted the discussion of x equals mu. They simply said that they exclude that case, but they didn't say why they excluded it. But if you include that possibility, you find that the cosine of the dihedral angle, which I call c hat here for convenience, can go to any constant between -1 and 1. And certainly the Neumann triangle construction certainly works under those circumstances. And the contact angle then will approach a certain value, which can be actually arbitrary between 0 and pi, and thus by no means necessarily must go to 90 degrees. And now, interestingly, this possibility x equals mu, which was not considered in the experimental paper, and this may have affected the conclusion also, this possibility is realized in a density functional theory using two densities, which is the minimum to make sense of this system, and using three phases that coexist. And this is a work that was done in collaboration with Kenichiro Koga. And what we found is that in a generic model for three-phase coexistence and for tricriticality, there are important gaps in the phase diagram in which there is no wetting, not even when you come close to the critical endpoint lines. And I can explain this, say, in this phase diagram, but that would take a lot of time because there are lots of things to say. But I can first, or rather instead, I can go to this line here, which is a critical endpoint line in the phase diagram. So states close to the critical endpoint line would have like alpha coexisting with beta gamma being the single critical phase that arises when beta and gamma become identical. So any point close to this line will be an alpha non-critical and a beta gamma critical phase. Now, if you start from, for example, this system in the middle here, which is a symmetric Mercedes star system alpha beta gamma with 120 degree dihedral angles, if you then approach a critical endpoint line, you will end up with some dihedral angles, one of which will be equal to pi, but the other one could be arbitrary between 0 and pi. And so there are a few that are sketched here. One is sketched here, in which you see that the dihedral angle for gamma is rather small, but finite. One is sketched here, in which the one for beta is non-zero, but still, here is one very symmetric situation, rather with a 90-degree contact angle, which is the one that Carl White and Busser concluded. But all the others also exist in this density functional theory. And the argument for their existence is actually surprisingly simple. Here we are close to this critical endpoint line that I indicated, so the beta gamma criticality, and I monitor the cosine of beta hat, and it varies between unity in the state where beta wets, and it goes to -1 and stays in -1 in the state where gamma wets. Okay, but of course there's a region here near the tricritical point where beta wets. But there's also a region further out where gamma wets. And you cannot just jump from one to the other. You must do this gradually, because all these functions in this model, and perhaps also in reality, all these thermodynamic functions are very smooth, continuous. There may be some singularities, but no abrupt jumps in, for example, the cosine of a contact angle, as you vary the bulk thermodynamic fields. I'm not saying surface field, but I'm saying bulk fields. And so this continuity, the continuity of the cosine beta hat is of course displayed very explicitly quantitatively by this calculation, in which we see a rather smooth curve between 1 and -1. And so all values of contact angles between 0 and pi are realizable. And there is then no critical point wetting between those particular temperatures in the phase diagram, which bound the gap, which bound the non-wetting gap. So this is an interesting result, we believe, from a density functional theory, which has some bearing on the experiment. See, because of course, if Carlwright and Busse would have included the possibility x equals mu, which they excluded, they would also have been able to discuss contact angle values not equal to 90 degrees, but anywhere between 0 and 180 degrees. And they would, of course, have concluded that they are not sure exactly which contact angle that they are observing, and that there is no strict necessity for them to be exactly 90 degrees. But now I'm speaking for them, and I should not do that. I should speak for myself. So what I believe that is happening is that these experiments better be revisited and redone with perhaps more accurate and more modern terms of observing the contact angles and doing measurements on them and determining exactly what is going on near the critical endpoints. So with this, it's already 4 o'clock, and I would like to conclude this part, and then tomorrow we will discuss another system, which is a colloid polymer mixture. It's a very interesting system which has been studied experimentally in great detail, and we have tried to do some theoretical work that helps explain and to some extent also predict what happens in those very beautiful experiments. So I hope to see you all again tomorrow, and especially Vincent, and wish you a very good continuation of this extremely sunny day with 28 degrees centigrade. It's called Vals winter in Afrikaans. So have a nice evening. Bye-bye.